All right, so B, 9B is focusing on velocity and acceleration as derivatives. So I hinted in A that when we were finding these average velocities, that it was a gradient, it was the slope of the line. And we know how to find gradients using derivatives. So we're going to spend a lot of time using that. So there's a little example here at the beginning. If I drive the 160 kilometres from Sydney to Newcastle in 2 hours, my average speed is 80 kilometres per hour. But my instantaneous velocity for the journey, as displayed on my speedometer, may range from 0 if I'm at a traffic light to 110 if I'm on the freeway. Okay? Just as an average velocity corresponds to the gradient of a chord on the displacement time graph, so the instantaneous velocity corresponds to the gradient of a tangent. So that's just saying yet again that if I am wanting to find the instantaneous velocity, it is going to be the gradient, which means I'm differentiating dx over dt, because these are going to be x equations. So we're differentiating the x with respect to time, and that will be the velocity of, or I can find the velocity equation and then use that to find actual velocities if I'm given times to substitute in. Now there's another type of notation that you will see in here. There's this middle one that has an x with a dot above it. That is a notation, it says down here, it was a notation introduced by Newton himself when we're differentiating these types of equations. So we will be using that quite a bit. It's much faster than writing out dx over dt all the time. The instantaneous speed, so that was for velocity. If you find a velocity, it's going to have a positive or a negative on it because it has a direction. If you are wanting to find the instantaneous speed, all you have to do is make sure you take the absolute value of that, which will get rid of any negative sign for the speed. When a particle is stationary, it means it is not moving. We say it is at rest, and this is when the velocity is equal to 0. When a particle is stationary, we let v equal 0, and then we can solve it to find out what the time is at that point. Acceleration is the measure of the rate of change of the velocity. Okay, so the velocity is the first derivative, so the rate of change of that velocity is going to be the second derivative. So acceleration is either the derivative of the velocity, which could be velocity with a dot above it, or here is my second derivative, x with 2 dots above it. Now, I don't tend to like dv's over dt's too much. I think the dot notation is far easier to use. So let's just write a little note here on the side. Remember that x is representing our displacement. We differentiate it once, and it's going to be the velocity. We differentiate it a second time, it gets 2 dots, and that becomes our acceleration. Now, you will also see that velocity is written as v and acceleration is a. Acceleration can be positive or negative according to which direction it is in. If a particle is moving to the right, it is positive. If it's moving to the left, it is negative. It's just like your Cartesian plane. Your numbers to the right are positive, numbers to the left are negative. When an object is not moving, it is at rest, so the velocity is 0. If the acceleration is to the right, this is acceleration now. Acceleration to the right is positive, acceleration to the left is negative. If the acceleration is in the same direction as the velocity, the particle is speeding up, or it is accelerating. If the acceleration is in the opposite direction from the velocity, the particle is slowing down or decelerating. If the object is travelling at a constant velocity, there is no acceleration at all, and you'll get a is equal to 0. There is a lot of stuff in there to think about. Units of velocity and acceleration. So meters per second or kilometres per hour. We're used to seeing them in that per notation. The people who do physics will be used to bringing that up, that s up, to be meters second to the power of -1 for velocity. Or for acceleration, meters second to the power of -2, because meters per second squared. It doesn't matter which one you use, they mean the same thing. So you can either write them with the per or bring them up with the negative power. Displacement, velocity and acceleration are vectors. They have direction and size. Distance and speed are scalars. They only have size, no direction. We've already talked about that many, many times. All right, let's go questions. Consider a ball that is hit vertically upwards. This is the exact same question that we did in 9a. It's the same equation. It's x equals 4t minus 10, bracket 10 minus t. Okay, this time they've given us the diagram, which fortunately looks just like the one we had before. So start at 0, ends at 10, turning point at 5, which goes up to 100. Okay, so we drew the graph right. Yay. What do we need to find out? It says differentiate our x equals equation and find the velocity when t equals 2, 5, and 8 seconds. All right, so differentiating. What should I do to differentiate this? Expand. Other option is a product rule, which we try to avoid if possible. Okay, so x equals 40t minus 4t squared. So when I differentiate it, let's use our lovely new notation. An x with a dot above it is for the velocity. That means velocity will be 40 take away 8t. Okay, we are asked to find that velocity at 3 different times. So I'm going to put it in a table so I don't have to have things subbed in all over the place. So my times that I was asked to find were t equals 2, 5, and 8. So this is just calculator practice now. You want to sub those numbers into this equation. So 40 minus 8 times 2 equals 24. 40 minus 8 times 5, 0. And 40 minus 8 times 8. Okay, what this is saying, what this is helping to highlight from our graph, for those of you who haven't done as much, I know there's people of varying experience with physics and these kinds of things. This point when t was equal to 5, but I've just shown at that point, which is my turning point, it is stopped. What is happening? The ball is being shot. It's actually going really fast at first. And as it's getting higher and higher and higher, gravity is causing it to slow down. So it starts slowing, it starts slowing, it starts slowing, until it gets to this point at the top where it's like, oh, I've got nothing left, gravity's pulling me too hard. It actually stops speed-wise, and then it will start going back down. And again, it will start slowly, and it will keep it, because of acceleration, it will keep getting faster and faster and faster until it hits the ground again. So anytime you are trying to find a turning point like that, you sub in that the velocity is equal to 0 and it will find that spot for you. Okay, on to the next one, part B. Use your graph to calculate the gradient of the tangents at 2, 5, and 8. So no calculus here. We have to use our graph. So we're going to have to flick back a bit. Maybe have your page turned out so you can see the graph. All right, so starting when time is equal to 2. Okay? If I am wanting to find the gradient, and that's why we had those tangent lines drawn on there. Okay, I didn't go back. Here we go. Oh, I didn't have tangent lines. I drew them on there. There we go. All right, I need to make a tangent line on there. So let's find time is equal to 2. Is here. Sorry, I thought I'd drawn them on there for you, but I hadn't. It's only on my one. Okay, here is time. Oh, it's not going to be perfect. We're working with a graph here. But let's try to, actually I'm going to fudge it a little bit because it should go through the 90. Haha. Going to make sure mine works well. Okay, so I'm going to draw a tangent. It's going to go from there. Going to touch the side of my graph at 2. And it's going to continue. I'm going to continue it. I'm deliberately making a line that's going to end at some nice grid points so that I can calculate a gradient. It's a little bit, I'm doctoring it a little, but it is a tangent. Okay, it's a tangent. But I just extended my line until it went through some nice grid points. Okay, so if I want to find the slope of that line, I need to do good old-fashioned rise over run. Okay, so the rise is, we're going from 90 down to 40. So 90 minus 40, and then the run is going to be from 3 to 1. You can draw the triangle if you want to. Does that help? There you go, you can draw the triangle in there so you can count the rise and the run. All right, let's go back to the spot. Okay, so we have the velocity was 90 minus 40, that was the rise, over my run, which was 3 take away 1. So measuring that tangent, I'm getting a velocity of 25. Hey, that's not too bad. Before we got 24. That's pretty close. Okay. Oh. Okay. Let's do the next one. We want t is equal to 5. Back to your graph. This is an easy one. Because t equals 5 is at the top, which should be a perfectly flat line. Which means my rise, no matter what I do, is 0. It doesn't matter what the run is. If the rise is 0, then the whole thing is 0. So back down here. When t equals 5, the velocity is 0. It's flat. And last one, when t equals 8, so let's see if we can do another tangent at 8. And again, try and make it go through some nice grid points. So there you go, I'm going to make it symmetrical with the other one. Oh, how far down did that go? Oh, yeah. Yeah, I drew it a bit long, but that triangle there. So it's 90 over 40 again, and 10 and 7. So back here, velocity is 40 take away 90 over 9 minus 7, which gives the negative 25. Okay, so they're not quite as accurate as doing it using calculus, but we are getting very similar results. We just had 24, positive 24 and negative 24 when we used the calculus. And it was much faster and way less of a pain. Okay, question C. What was the initial velocity, which is the velocity where the ball was originally hit, which means time is equal to 0 seconds. Okay, so we are subbing in that time is equal to 0 into where? The derivative, because it wants the velocity, which is the x dot equation. So the equation was, where did it go? X dot equaled 40 minus 8t. And if I sub in that t is equal to 0, what do I get? 40. Good, meters per second, even better. Question D. What is the impact speed when it hits the ground? What was the time when it hit the ground? 10. So I'm subbing that t equals 10 into my, which equation? The derivative against the velocity, but it asked for a speed. So I'm going to find the velocity first and then just make sure I go in my answer. Therefore, it needs to be a positive answer. All right. So in my equation, it will be v equals, not v, I'm doing x dot. X dot equals 40 minus 8 times 10. Which gives you a negative 40 meters per second, because that is velocity. But because of the wording of the question, it is important that I give the answer that I need. It asks for a speed. So I'm going to say, therefore, impact speed is a positive 40 meters per second. You take the direction out of it. The negative means it was coming down. Obviously, it was coming down. It's coming down to hit the ground. But we just want it the 40 meters per second. E. Still a lot of chatter. Oi. Save it for later. Find the acceleration function A and sketch the acceleration function. So they're calling it A, so I better do that. But remember that this is the second derivative. I'm going to put it next to it. This would be the x with the double dot. Okay? So I have my, I've written up here, which is nice. This is my first derivative, the 40 minus 8t. I want to differentiate it a second time to find the acceleration. What's the derivative? -8. So it doesn't matter what time is when you're talking about acceleration for this particular equation. Acceleration is always going to be -8, and that would be in meters per second squared, or meters seconds to the -2 if you prefer. Yeah, it's not changing with respect to time. It's always a constant acceleration. If I want to draw that, it's going to be a horizontal line. Make that neater. So this time we are sketching, here is my time axis, and I'm sketching acceleration. So acceleration is going to be the vertical axis. I'm going to change colors so you can see it. I want to have A equals to -8. So you go to your A axis, you find the -8, which is going to be down here, and you draw a line, supposed to be going through it. So there is my acceleration graph. F. Find and describe the displacement, velocity, and acceleration when time is equal to 2. Okay, so we're just subbing those in to the 3 different places. We want displacement, we want velocity, and then we're going to have acceleration. Actually, acceleration has 2 C's, doesn't it? Whoops, there you go. Squeeze it in there. Okay, so time equals 2. Sub that into our 3 different equations that we have. The displacement equation was x equals 40t minus 4t squared when I expanded it out. I'll write it down. 40t minus 4t squared. If you look back in the pages, you'll find that back at the beginning. Okay, so we sub in that time is equal to 2, so 40 times 2 minus 4 times 2 squared. That makes 64 meters. It does say and describe. Okay, so I probably should make a little bit more of an effort here. If I want to describe that, I would say the ball is 64 meters above ground. Positive direction, above ground is what that means. All right, now let's do the velocity. The velocity equation was, where did it go? It was 40, I should just differentiate again, 40 minus 8t squared. Oh, t, not t squared. Okay, sub in the 2, and we get 40 minus 8 times 2, which is 24 meters per second. What does that mean? Describe. Which direction? Give me a description. Going upwards. So it's still moving in the going up direction. So velocity is 24 meters per second upwards. Okay, acceleration, there's nothing to sub in. Acceleration was always and is always -8 meters per second squared. Okay, which means that it is decreasing. The minus means that it is decreasing, it is decelerating, it is slowing down. The particle is decelerating at 8 meters per second squared. That is the whole way through the trip. The fastest speed that ball is ever moving at, and you can think about this because negatives are different direction, the fastest positive speed that it is ever moving at is when you initially throw the ball. After that, it is slowing down all the way to the top, And then the velocities as you go to the other side, yes, they're getting steeper, which means they're getting more negative. Getting more negative means they're still getting less and less and less and less, right? So it is slowing down the whole time. All right, so there is one last little describe thing here. State when the ball is speeding up and when it is slowing down. Explaining why this can happen is when the acceleration is constant. All right, this is speed versus velocity though. If I was talking about the velocity, it is slowing down the whole time. If I talk about speed, it starts really fast, it slows down to the top, and will speed up again as it goes back down to the ground, because speed doesn't have a direction that the velocity has. All right? So we need to try and put a description in there of when the ball is speeding up and slowing down. So I'm going to use the word speed, so I'm going to start with that little description of speed. The ball starts fast and slows down to 0 at 5 seconds. Then speeds up, or should I say getting faster, speeds up until it hits the ground. At 10 seconds. Do we want to say more about velocity, or is that just for our own information? It didn't ask about velocity. Oh, Tyler's just turned the page. She's like, no, I'm done with this question. You understand that velocity is different though? Okay. Yes, all right. Question 2, let's keep moving. Yes, there is a few more. This one's the long one. A particle moves so that its distance, new question, starting again. A particle moves so that its distance in meters from the origin at time t seconds is given by our lovely new equation. Here it is. Find the velocity and speed when t is equal to 3. Okay, I've got a displacement equation. If I want velocity, I'm going to have to differentiate. So let's use the V symbol this time. We're going to get used to both. So V for velocity, differentiating, bring the power of 3 down. 3 times a third is just 1. So it'll be t squared minus 10t plus 16, and the constant disappears. Okay, now I'm wanting to sub in when t is equal to 3. The velocity will be 3 squared minus 10 times 3 plus 16. What does it equal? -7. No. -5? -5 meters per second. That is the velocity. The speed would be just without the negative sign. So velocity, I keep putting, velocity is -5 meters per second. Speed would just be 5 meters per second. Take the direction out of it. Part B, find the times when the particle is stationary. We've read this plenty of times. It is stationary when the velocity is 0. Velocity is not moving. So when V equals 0, my equation was t squared minus 10t plus 16. That was my velocity equation. Now solve it to find the time. Came straight from here. Velocity 0. -8 and -2, yes. Yeah, it seems very... Oh, is that the same? It's definitely starting equation. It's the same numbers. All right, so t equals 8 and 2 seconds. Find, boys, find its distance from the origin at this time. So that's going to be going back to the displacement equation, and we want to sub in that time is equal to 2 and time is equal to 8. So I'm going to split it in half here. So this will be the when t equals 2, and this will be the when t equals 8. And we're talking about, as I said, distance. So this is our displacement equation, which is the one up at the very top. So it will be x equals 1/3 times 2 cubed minus 5 times 2 squared plus 16 times 2 minus 8. Who's working ahead of me? Got that? 6 2/3 of a metre is what I had. Do the same thing with the 8. So 3rd times 8 cubed minus 5 times 8 squared plus 16 times 8 minus 8 equals -29 1/3 metres. Now, those are actually displacements. Okay? So if we want to be clear that we want these to be written as distances, I could say that the first one here is 6 2/3 metres to the right of the origin, so it's a positive direction. Whereas this one is a negative, oh, I'm just going to say 29, get rid of the minus. It's a 29 1/3 metres to the left of the origin, or the negative direction. But those are the distances without the direction. Find the acceleration of the function and find when the acceleration is 0. Okay, to find acceleration, you have to differentiate the velocity. Where's my velocity equation? Back here. T squared minus 10t plus 16. So acceleration will be 2t take 10. Sub in that the acceleration is 0. So 0 equals 2t take 10. So time is equal to 5 seconds. That's all we need to find for that, I think. E, where is the particle at this time? Where? When I say where, what is that talking about? Acceleration, velocity, displacement. Displacement. I want to know the displacement when time is equal to 5. Back to my displacement equation. That's the one with the 1/3. 5 cubed minus 5 times 5 squared. 16 times 5 minus 8. And that's a -11 1/3 metres. All right, so the question was, where is the particle? It is -11 1/3 metres from the origin. And what is its velocity? So I want to know its velocity as well. So sub it into the v equation as well. So that was the t squared one. So it's 5 squared minus 10 times 5 plus 16. So I hope you find it's not, as long as you know acceleration, velocity and displacement, the math, the calculations that we're doing aren't overly complicated. Just be careful to make sure that you're not missing the details. So I might write a little description for this one. So it says, where is the particle at the time and what is its velocity? The particle is 11 1/3 metres to the left, because it was negative, with a velocity of -9 metres per second, which also means direction, negative direction. All right, question 3. How many more of these we got to go? 3 and 4, still 2 more. Okay, so you have now learned to differentiate lots of different things. So that could mean at any time you would have to differentiate trig functions or exponentials or normal things. Okay? So here is one that brings trigonometry into it. A particle's displacement is x equals 2 cos pi t. Find its find its velocity and acceleration. Do I need to stop? Find its acceleration and velocity as functions, and then graph all three functions for the interval of time between 0 and 2. Okay, all three equations. The first equation is the displacement, which we've been given. Okay, it was x equals cos t. Okay, before I go on to velocity, I'm going to have to draw this. So what do we know about this graph? I want to know the amplitude, yes, and I want to know its period. So the amplitude is what? 2. The period of the graph is what? It's 2, because you take the normal period of the graph, which is 2 pi, and you divide it by any number that's in front of the t, which is the pi. Okay, so that means that we're left with a 2, which is convenient because that is here. So we are going to draw this cos graph over here on the side. Might as well finish the whole graph before we move on to the next one. So we have time. We're going to have 0, 1, 2. So there's 1, there's 2, but I've marked the halves in between because that will be helpful to drawing it. The amplitude is 2, so it's going up to 2 here, down to -2. The cos graph starts at, well, normally 1, but this time it's going to start up at 2. At the end, it's going at 2, which is 1 period. It is still going to also be at 2. In the middle, at 1, it will be down at -2, which means that these half and 1.5 is where it's cutting through the axes. So draw the curve. All right, that was the easy one. Let's move on to the next ones. Next, we want velocity. How do I differentiate 2 cos pi t? Yes, find your study sheets. It is negative. Negative what? What happens with the 2 and the pi? T, what happens with those things? Whatever is in here, the derivative of whatever's in front of that t, it needs to come out the front. So it's going to be -2 pi, cos changes to sine of, do I change? It's pi t. You don't change the function. The derivative of the function comes out the front, but this part should never change. Okay, then I want to know the amplitude and period, because I have to draw this graph as well. So the amplitude is what? 2 pi or -2 pi. Depends how you want to think about it. And period is 2 again, because again it will be 2 pi divided by pi, which is still 2. All right, so let's draw this one up. So this is a time and velocity graph. So put a V on that axis. This last one should have been an X because it was the displacement. And we're going to have 1, 2, and put the halves in there as well. This time my amplitude is going to be 2 pi and -2 pi. So that -2 pi, we're drawing sine, is going to change, it's going to reflect it over the x-axis. Normally my sine graph starts at 0, which is still will. It's going to end at 0, and halfway through it's going to be at 0. Normally it goes up and comes down. But because of this minus sign, it's going to go down and then go up. Okay, it's reflected it. So up, down here, to up there. So we go down, up. There's a little bit, one looks not quite to scale, but anyway. All right, one more, acceleration. Oh, I'm running out of room. Okay, differentiating my velocity equation. Differentiating sign, you get positive or negative. It usually stays positive, which means the minus sign that is there is going to stay there. It'll be negative still. What's going to happen with stuff out the front? There's another pi from here that's going to come out. So it's going to be negative 2 pi squared, changes back to cos of pi t. What is the amplitude? Yeah, so the negative 2 pi squared, and the period is still 2. Okay, I'm not going to calculate that again. One more graph. This will be time and acceleration. We have 2 pi squared and negative 2 pi squared. I'm going to make it small because I'm running out of space. 1, 2. Okay, so cos normally starts at 1, but for us would be 2 pi squared. But because of the minus sign, it's going to start down here. It's been reflected again. So starts down here, which means at 2, it's going to end in the same spot. At 1, it's going to be at the positive 2 pi squared. And it's still going to go through half and the 1.5. So it'll go up, over, and down like that. And then we have some things to describe, I think, for the next few parts. Find the times within the time interval between 0 and 2, which is what we've been looking at, when the particle is at the origin. Find its speed and acceleration at those times. When is my particle at the origin? Now, this is talking about the displacement. I have not moved from the origin, so that means my displacement is 0. Where is my displacement 0? Look at your displacement graph. When time equals half, yes. Is there any others? Yes, and time equals 1.5. Okay, so there's 2 spots. Well, half and 1.5. Now for each of those, I have to find the speed and the acceleration at those times. So speed, I'm looking at the velocity graph, and acceleration, I'm looking at the acceleration graph. Okay, so that's going to go to a velocity of, oh, it said speed. That's a bit naughty, isn't it? Ooh, okay. Speed. I wanted to do velocity. Okay, if it asks for a speed, let's start with velocity. What is the velocity at half? Negative 2 pi. But because it said speed, I'm just going to write 2 pi. Yes, it would be. I'm not putting units in here because I've got very limited space. Let's do the speed for the 1.5. The 1.5 is here. So it was up the top at the positive 2 pi. So they actually have the same speed, but their velocities were different because one was negative and one was positive. Okay, let's go to accelerations. The acceleration at time equals a half was, acceleration graph, 0, and at 1.5, 0. 0 for both of them. Part C, what else do they want us to find? Find the times within the time interval when the particle is stationary. What does that mean when I say the particle is stationary? When what? What equals 0? Velocity equals 0. So look at your velocity graph. Tell me where the velocity is 0. At t equals 0, t equals 1, and t equals 2. Because at those points, it says find its displacement and its acceleration. At least it's displacement this time. I don't have to, I can leave my directions in there. So, going to your displacement graph, what is the displacement at 0? 2. What is the displacement at 1? Negative 2. What is the displacement at 2? Back to 2 again. Good, all right? Then we want to do the acceleration for each of those. These are little commas for the next bit. So the acceleration at time equals 0 is, yes, negative 2 pi squared. Acceleration at 1. Nope. 2 pi squared. Is Lewis the only one doing this? Acceleration at 2. Negative 2 pi squared. Good. Thank you, Grace, for helping. Briefly describe the motion. Who wants to try that? Yes. Technical word for up, down is oscillates, but like it. So it is oscillating between -2 and 2, all of them, with a period of 2. It says describe the motion. So I was, yes. And it begins, the displacement begins a distance of 2 and moving towards the origin. There's so many things you could say, but it does say briefly. All right, so here was mine briefly. You could describe the displacement. You could describe the velocity. There's so many things you could describe. Oh, I was doing similar things over there, but they're not. Okay. Oh. There's many more things, but it did say briefly. And I think you guys are losing concentration. Not at all? We ready for 4? You're still writing? That's 1. All right, question 4. A particle is moving so that its height, x meters above the ground at time t seconds, is given by x equals 3 minus e to the negative 2t. So here comes the exponential now. All right, find the velocity and acceleration of the functions and sketch the 3 graphs, just like last time, but with an exponential. It's just remembering all the stuff we've learnt, right? It's revision class, really. Displacement. What you find is that the more topics you do, especially if you guys are heading up to the HSC now, it stops being, this was a trigonometry topic, this was a differentiation topic, this was a exponentials topic. And it's like, they all go together. Everything can all be used in all sorts of different ways. They don't necessarily have to be divided into categories. All right, so the displacement, what is wrong? Okay, there's my displacement equation. How do you draw that? Okay, a normal exponential curve goes up, okay, but this one has got a minus here and here. What does that do? It's going to reflect that way and that way so that it's going there. Oh, wait. Which way am I going? Yeah, that way. Okay, and then what does the 3 do? Moves what up? Yes, but thank you. The asymptote, there's normally an asymptote at y equals 0, so it will now be at y equals 3. So that's a very good place to start. So here is my graph, time. Here is my asymptote, which is at 3. So probably a good reference point would be to find that, it's not a y-intercept, it's actually an x-intercept, but you know what I mean. That vertical intercept. What would I do to find it? Sub in that, time equals 0 to find that intercept. So when t equals 0, x equals 3 minus e to the 0. So 3 minus 1, because e to the 0 is 1. So it's 2. So there is my intercept. And we don't have negative time, so we're not going to continue this graph down here, but it's going to be coming up and approaching that asymptote. Okay, so it looks something like that. Let's move on to velocity. Differentiate the equation. The 3 will disappear because it's a constant. How do you differentiate negative e to the negative 2t? Bring down the negative 2, so it will become a positive 2 e to the negative 2t. Good. So where is the asymptote for this? Has it been moved? No. So this one has its asymptote back at 0. So change of colour so we can see the asymptote. There it is. I should write those on the thing, shouldn't I? Horizontal asymptote at y equals 3. Horizontal asymptote at y equals 0. And this is a t-axis and a velocity axis. Okay, what would be my intercept? Because we always need to know when time equals 0. Okay, so put time equals 0 in, which will be velocity equals 2e to the 0, which is 2, which is like just before, starting at 2 here, but this time its velocity is getting slower. It's getting closer and closer to 0. It's slowing down. And last one, acceleration. Differentiate again. What's the derivative? Negative 4e to the negative 2t. Okay, let's just, before we draw it, let's just straight away sub in when t equals 0. So we have our intercept. So acceleration would be negative 4e to 0, which is negative 4. My asymptote is where? Yep, 0, because I haven't moved that. Horizontal asymptote is y equals 0. The intercept was at -4, and it's going to be coming up to that, getting close to that asymptote. So it is actually, its acceleration is moving in the positive direction. It's going from a negative and getting bigger at a decreasing rate because it's slowing down. Don't you love those words? Increasing at a decreasing rate. So I mess with your brain, Lewis. Oh, I think we're going to do that down here. I think that's one of the things coming up. All right, question B. Find the initial values of displacement, velocity, and acceleration. Oh, I already did that. We can just write those straight down. So the initial displacement was 2. Was it meters? Do we have the units? Yes, meters. The initial velocity was, Will, what was it? Yeah, you weren't listening. David will help you because he was listening. Thank you. 2. That would be meters per second. And the acceleration is negative 4 meters per second squared. All right, question C. What happens to the displacement, velocity, and acceleration eventually? Eventually means as we're going to infinity. As time is going to infinity. You always laugh at me. As time approaches infinity. Now, it's going to be different for, you've got 3 different ones to do. All of the equations have the e to the negative 2t in them. So what happens if you put infinity into that? It gets bigger because e to the negative infinity, basically. So that would be approaching 0. So anywhere where you see that e to the negative 2t, it's approaching 0. So let's look at our x, v, and a. The x equation was 3 minus e to the minus 2t. It's up here. There it is. Okay, so this part here is approaching 0, which means my graph is approaching the 3. It's basically where the asymptotes are. Okay, so the graph is for displacement is approaching 3. For velocity, it's approaching, nope, 0. And for acceleration, it's approaching 0. Last one, we're nearly there. Briefly describe its motion. The particle starts, I'm going to write it as I say it. The particle starts, it's always good to know where you start, 2 meters above ground. So that's displacement. With an initial velocity, so all the initials, of 2 meters per second upwards, it is constantly slowing down. That's talking about the acceleration. I made reference to displacement, velocity, and acceleration. As it moves towards a limiting height, oh, look at these fancy words, of 3 meters. That about sums it up, doesn't it? Woo woo.